I will be talking about the axion domain of formations and the cosmological and the phenomenological implications. In particular, I want to show that the domain wall can be formed in string axiverse, and therefore the implications of the domain wall may be an indirect proof of the string axiverse. So this is the plan of today's talk. I prepare for this four part. So introduction. First of all, I want to remind what is axion. So I think in general, we can define the axion as follows. So axion has a periodic field space satisfying this condition. Here, F phi is the decay constant, and it represents the size of the physical field space of the axion theory. In addition, we have some approximate shift symmetry. So this is the definition of axion. From the first condition, we can say that the action potential should be periodic. From the second condition, we can say the energy scale for the action potential is much smaller than the decay constant. And we can also predict that the axion should have mass much smaller than the decay constant. This kind of axion can be found in various UV completions, like the spontaneous symmetry breaking of global U1 or Pechekin symmetry. Also, we can find the axion from the compactification of the extra dimensions in string theory or M theory. Given the previous definition, we can say that in any axion theories, we have stable domain wall configuration. This is because we have periodic potential, and because we have the approximate shift symmetry, the potential must be bounded above and below. Therefore, we can have minimum, and once we have one minimum, then we have degenerate another minimum due to periodicity. This minimum may be physically equivalent, but in any case, we can connect the two minimum to form a domain wall configuration. Sometimes we can have more degenerate vacua due to the depending on the property of the non-perturbative effect to generate the potential. The number of the degenerate vacua in the physical field space is called domain wall number. For instance, if we consider this kind of potential, then we can find the setup with domain number 2. So basically, within the physical field space, we find 2 minimum. Connecting the adjacent vacua, we can again get the domain wall configuration. Those domain wall configurations can be populated in the early universe depending on the cosmological history. One well-known possibility is the phase transition of the approximate U1 symmetry. In this case, as we can produce some string and domain wall system. Depending on the domain wall number, we can have different kind of the network. It is known that when the domain wall number is unity, then this network is not stable, but for the domain wall number equal 2 or more, we have stable string domain wall network. Of course, this kind of scenario is only applicable to the U1 SSB UV completion. Today, I will focus on another possibility. This is the domain wall formation from the inflationary fluctuation. Actually, this scenario works within the axion EFT, so it can apply to not only the U1 SSB case, but also to some string M theory axions. The interesting thing is that in this case, we have a domain wall without a string. So I will explain how to form the domain wall from inflationary fluctuation. Let's first consider the axion is light enough during inflation. Namely, the mass of the axion is much smaller than the Hubble parameter during inflation. Then since axion is a scalar field, it undergoes random jump during inflation due to the Dojita space dynamics. Therefore, after inflation, we can only tell the axion field value around the certain position in the universe in a probability way. The probability distribution can be characterized by two parameters. One is the average field value in the observable universe. The other parameter is basically the Hubble parameter. It can represent the variance of the distribution. More precisely, we can calculate the power spectrum for the axion fluctuation in the non-vanishing mode for the momentum. Then we can find that the power spectrum basically scale invariant. This is similar to the inflation theory. The inflaton fluctuation in inflation theory. So, of course, whether the domain wave formation happen depends on the parameter set. Let's first consider the average field value for the axion is 0. Namely, it is around hilltop. And let's consider the cosine type potential. Then we can find that in the half of the universe, we have the axial field value closer to the left vacuum. In the another half of the universe, we have the axial field value around the right vacuum. So those kind of distribution is mixed up. So at some point we will have the axial start to oscillate around the left vacuum when the mass becomes comparable to the Hubble. At another point x2, we will find the axial start to oscillate around the right vacuum. Then connecting x1 and x2, we will find the domain wave configuration. Since we have many, field, many positions and many axion distribution, therefore we can have many domain walls. Then those domain walls will gradually form the scaling solution. So we have order 1 domain walls in 1 Hubble volume. In this kind of formation of domain wall, we don't have cosmic string because this is kind of similar to the Z2 symmetry breaking case. In spontaneous Z2 symmetry breaking, we have domain wall, but we don't have cosmic string. So this is a basic mechanism for the domain wall formation from the inflationary fluctuation. However, it was considered that this kind of formation will provide domain wall network not stable unless we introduce serious fine tuning. This is because the field value, the average one, is naturally non-zero due to the random jump behavior during the inflation. And if this is non-zero, then we need to consider population bias. And it was numerically estimated that population bias makes the domain wall network soon decay, even if this population bias is 1% or smaller than 1%. Therefore, it was claimed that we need fine tuning. But today I will show this is not the case for the inflationary fluctuation. And in fact, we don't need significant fine tuning for the domain wall network. Okay, so I will show the stability of the axion domain wall network from inflationary fluctuation. And by using this stability, I will consider the string axion domain wall formation by using the inflationary fluctuation. Okay, to show my claim, I would like to employ lattice simulation for the domain wall evolution. To this end, I will consider the simplified setup with Z2 symmetric FIFO potential like this. So this is actually the system that was studied in the previous works. And I think this is a good approximation for our purpose because around the hilltop, we can expand the cosine term up to fourth power like this. And the relevant field length for the domain formation is around the hilltop. In the following, I will solve the equation motion from this kind of potential by assuming two kinds of initial condition. One initial condition is characterized by white noise, or this can be considered as the initial condition respecting the thermal fluctuation. And we can say this is the initial condition with causality. So if we consider the super horizon scale, we will find that the real space correlation function is vanishing. Therefore, by Fourier transformation, we have this kind of white noise spectrum. On the other hand, if we want to study inflationary fluctuation, as I said, we need to consider scale invariant initial condition. And this is, beyond the causality. And thanks to this behavior in the inflation theory, we can solve the horizon problem. And this kind of behavior also applies to any, light degree of freedom during inflation, including the axiom that we are interested in. So the new point of our work is to, take into account this kind of power spectrum as the initial condition for the fluctuation. Then we solved the equation motion, and I showed the numerical result for the snapshot of the domain wall configuration at the long enough time. Here, for a while, I consider the population bias is 0, and indeed we can find that in both cases we have the scaling solution. Namely, we see in order 1 have a volume, we have the order 1 domain wall. But we can see that the structures are quite different. In the white noise case, we can have the structure with scales around the Hubble size. But in the scale invariant case, we can have many scales of structure. For instance, here we can find a very large void. We can understand this large void. Of course, these large voids are from the scale invariant initial condition, but we can understand it from the aforementioned random jump behavior. So out of in the whole simulating box, we have vanishing population bias. If we want to focus on this slightly smaller, box, we will have some random jump. Therefore, naturally, the population bias in this smaller box is non-zero. It may be towards to the left vacuum. If we focus on here, we have random jump because it is random, so we may also have the population bias towards the right vacuum. Therefore, we can have large vacua, large voids towards the left vacuum or right vacuum, and then we have a large scale of the domain wall. This kind of domain wall rarely decay, disappear because they have the super horizon size. From this kind of argument, we can also expect that the domain wall network should be long-lived even with non-vanishing population bias. This is because we can consider this kind of configuration and we enlarge the box. Then we consider larger size. Then we have again random jump behavior. In average, we will have the population bias non-vanishing naturally. It is order 1 naturally. And since this larger box include this kind of configuration, which is stable, then we can say that even with the non-vanishing population bias, we can have the relatively stable domain wall network. This is a numerical simulation result for the non-vanishing population bias. Again, left-hand side represents the white noise case, the right-hand side represents scale invariant case. Horizontal axis is the conformal time with certain normalization. The vertical axis is the domain wall length per unit Hubble scale. So we can say this is the area parameter in 3D case. But here I show you the 2D simulation for simplicity. And actually we have calculated also in the 3D case, and the conclusion do not change. So the difference of the two figures are listed the contours. For in the white noise we list the contour with the listed line correspond to the population bias smaller than order 1%. Even with the population bias smaller than order 1%, we can find that this kind of domain wall network decays. So the typical length is, becomes smaller in time. On the other hand, in the inflationary fluctuation case, even with the order 1 population bias, we can see that really the length decay. Therefore, we can conclude that the domain wall network from inflationary fluctuation is actually stable if the population bias is smaller than order 1. The key point is, again, we take into account the super horizon modes. Okay, given the stability and against the population bias in the inflationary fluctuation case, we can discuss the scenarios for the domain wall for network formation. We need to consider the scenario satisfying this condition, population bias smaller than order 1. One possibility is to consider the decay constant is around the Hubble parameter. The distribution of the action field, have barriers covering the almost all of the field space. Then it also cover the hilltop, and it naturally satisfies this condition. But we need to be careful because the Hubble parameter during inflation is known to be smaller than order 10 to 13 GeV from the observation of the tensor, bound from the tensor to scalar ratio from CMB data. So this implies that the decay constant for this scenario should be smaller than this value as well. But if we consider certain UV completion, usually we have the decay constant to the expectation value of the dynamical field. And if this dynamical field, say the Petriquin Higgs, is light during the inflation, then this Higgs may get some Hubble-induced mass, then we may have this kind of relation during the inflation. And later, we have the decay constant larger than Hubble or smaller than Hubble. In this case, we can still have successful domain wall formation. Another possibility is to have many axions. So all of these Hubble parameter is smaller than the decay constant. If we have many axions, some of axions can have this condition satisfied. In the case we don't have very large the Hubble parameter, and we don't have many axions, we may consider so many axions. We may consider mixing between a few axions. For instance, if the Hubble parameter is relatively small, and this Hubble parameter is due to the axion inflation, then the other axion that is not inflaton is naturally settled around the minimum. Then if there is mixing after the inflation, we can flip the potential to make the non-inflaton axion to have the axial field around the hilltop due to the shift of the field value. Then we can have the domain wall formation. And interestingly, the first three possibilities do not depend much on the axion potential shape. Even if we consider this kind of shape with the periodicity guaranteed degenerate vacuum, we can form the domain wall. In the inflationary case, it doesn't matter what is the population bias as long as it is not too large. Then even with this kind of potential, we are sure that we can form the domain wall, which is stable. Okay, now we are ready to discuss the string axion domain wall. And in fact, in the string axion, it may be natural to have the decay constant to be around 60 GeV unless we consider some large volume compactification. If we focus on this possibility, we can still have the domain formation because in string axiverse, we may have many like axions. If the like axion number is actually larger than the decay constant divided by the Hubble parameter, for instance, if the Hubble parameter is 10 to 13 GeV and decay constant 10 to 15 GeV, so we have the threshold around 100. So if the axion in the string axiverse is larger than this value, it is unnatural to have all of the action without domain wall. Some of the action must be around around here naturally. Then we can have the domain wall formation. Even if we don't have many, so many axions, we may have some mixing effect induced by the several axions, and then again we can generate the domain wall network. So I want to say that in string axiverse, it may be natural to form the domain wall because in string axiverse we have many axions basically. Then it becomes more important to discuss the cosmological implication and phenomenological implication of the domain wall network because it can be an indirect proof of the string axiverse. If the domain wall network is stable, then we have domain wall problem because it easily dominate over the universe. So we need to solve the domain wall problem. And solving the domain problem will give some implication, and that will be that may be proved in the future. One possibility is to consider the domain wall network decays due to some, say, some population bias. Then the decay of positive domain wall will produce the gravitational waves, and this gravitational wave could be proved. First, I will discuss this, and later I will discuss another possibility. This is the case that the tension of the domain wall is small enough so that it never dominates over the universe until today. And then it means that the domain wall still exists around present universe. If there is certain coupling to the some of the particles, then we can have some implication. For instance, if the domain will cover the photon, we can have a cosmic birefringence. To discuss the domain wall network decay, let's consider this kind of concrete potential. So the first one is the potential with domain wall number 2. So it has degenerated vacuum which are not physically equivalent. The second term is the domain wall contribution from domain wall number 1 potential, and this lifts one of the vacuum that was degenerated due to the in this potential. When the tension of the domain wall multiplied by the Hubble parameter is equal to the potential bias, we can find the domain wall network dominantly collapse, and we can solve the domain wall problem and produce the gravitational wave. And this kind of gravitational wave may be proved. And I think this is kind of interesting scenario. In fact, so far there was no complete numerical study by including this potential bias. People usually study the gravitational wave from the domain wall network, namely with the potential bias 0, and then we cut the domain gravitational wave spectrum at a certain period to which is relevant to this condition, and to predict the gravitational wave. The difficulty for numerical simulation with full potential may be as follows. So if we want, with the full potential, if we want to have a scaling solution, which we need to have the potential bias to be small enough. If we want to have the population bias small enough, we need to have a very long calculation time for the most of the domain wall to collapse. Then, in expanding universe with the fixed conmoving volume analysis, we need to pay the price of the resolution. So we have several requirements contradicting with each other. With this background, we provide the first lattice simulation of the gravitational wave from decaying domain wall by taking into account the not only the usual potential, but also the potential bias. The key point or the trick of our analysis is the time-dependent bias. Here we consider at the beginning the bias is 0, and then we turn on the bias after the scaling solution is formed. And because the bias is large, then the domain wall can soon collapse in a short time. Therefore, we can satisfy the previous requirement. Of course, this is not completely consistent with the case with the constant bias, but it is very good approximation if we consider really the potential bias is time dependent. This is the case if the domain wall appears a potential bias similar to the QC reaction-like potential, which depends on the cosmic time. So this is a numerical result for the gravitational wave spectrum. And here I show several lines, and the different line corresponds to the different time slices for the gravitational wave spectrum, and time increases in this direction. For the first few lines, we don't have the potential bias. Therefore, the spectrum is completely from the scaling of gravitational wave, and we can find the peak following the uh, uh, the horizon side. On the other hand, we can find another contribution around here, and this contribution turned out to be dominant. This is because we consider this kind of new contribution is coming from the last moment collision of the domain wall. In the last moment, this domain wall is accelerated due to the first vacuum energy. Therefore, they are energetic. So the collision will provide energetic gravitational wave. So it provides dominant component. Therefore, by taking into account the potential bias in the numerical simulation, we found a new contribution for the gravitational wave, which is dominant. This is the case for the scale invariant case. We also apply our analysis to explain the nanograph data. Nanograph data is naturally explained if the axion domain wall coupled to the QCD. Then, due to the QCD phase transition, we will provide the time-dependent potential bias. And only at the QCD phase transition, we have the potential bias. Therefore, the domain wall decay must happen around the QCD phase transition, predicting the nanohertz gravitational wave. Unfortunately, it is unlikely to be a string axion because we need to have the decay constant small enough to have the axion produced from the domain wall collapse to decay before the BBN. So this is too small to be a string axion. But in general, we can have the string axion domain wall to collapse to produce a gravitational wave that will be that may be proved in the future. Another topic is about the possibility for the small tension, and I may not discuss in too detail, but so we consider the axion coupled to the photons, and in this case, it is known that if we have the background change of the axion field, we can have the photon polarization rotate. In particular, for the CMB photon, we can have the cosmic birefringence. And cosmic birefringence have two kinds of observable. One is the isotropic cosmic birefringence. This has actually 3 sigma hints, which is non-vanishing, interestingly. And another is the anisotropic cosmic birefringence. For instance, we can consider the power spectrum of the rotational angle. In fact, the scaling domain wall without a string can naturally explain the isotropic cosmic birefringence. This is because the domain wall basically separate the field value by pi f phi, and then we have a solid prediction around 0.1 degree of multiplied by the anomaly coefficient. And if this kind of isotropic cosmic birefringence explain the data, then we predict the anisotropic cosmic birefringence, because in the last scattering surface we have many domain walls, and this kind of domain wall contribute to the anisotropy of the cosmic birefringence. And from the numerical simulation, we found that for the scale invariant case, we can soon prove whether this is the case. For the white noise case, we may need to wait for several years until the CMB stage 4 data to be released. And in this case, we can still prove this kind of scenario. Okay, this is the end of my talk. In my talk, I wanted to say that the axion model usually involves stable domain wall configurations. And in particular, in string axiverse, we may also produce the domain wall due to the inflationary fluctuation. In particular, this is because in string axiverse, we have many axions. And then we need to be careful about the domain wall problem. Avoiding the domain wall problem by potential bias, we may produce a gravitational wave. And actually, from numerical simulation, we found a new contribution to the gravitational wave. And in the future, we may search for the gravitational wave to search for the string axiverse to prove the string axion. On the other hand, we may avoid the domain wall problem by small tension, and then we may if this action coupled to photon, then we may prove it from the cosmic birefringence. In both cases, our scenario apply to the case of decay constant of 16 GeV, so they may be an interesting proof of the string axiverse. Okay, thank you very much.